So this is a joint work with Udan Dorji, Márton Elekes, Kende Kalina, and Viktor Kis. And this is a very much ongoing project, so there will be a lot of questions. I will start with a very short introduction to Fraisse limits. In this talk, I will consider mainly relational structures, countable relational structures. This means that we have a countable set, and we have countably many finitary relations on this set. We call such a structure ultra-homogeneous if every isomorphism between its finite substructures can be extended to an automorphism of the whole structure. Okay, and the age of a structure is just the collection of the finite substructures. And we say that a set of finite structures is a Fraisse class if it has the following three properties. If we have a structure from the class and we have a substructure of this substructure, then the substructure is also the element of the class. The second one is the joint embedding property. So if we have two structures, then there is a third one, so that these two structures can be embedded to the third one. And the third property is the amalgamation property, which is we have three structures, okay, B, A, C, and embeddings. Then we can find a fourth structure D, so that and two embeddings such that this diagram commutes. Okay, so this is the amalgamation property, and the famous theorem of Fraisse says that a class is Fraisse if and only if it is the age of some ultra-homogeneous relational structure. And in this case, we will call this structure the Fraisse limit of our Fraisse class. And some easy examples. For example, if we take the collection of finite sets without any relations, then their limit will be an infinite set without relations. Okay, a little bit more interesting, if we take the finite linear orders, then their limit is the rational numbers with the usual ordering. And if we take the collection of finite graphs, then the limit will be the random graph or Redó graph or Erdős-Rényi graph, which is the following. You take infinitely many vertices, and to decide the connection between two vertices, you flip a coin. So this is a probabilistic construction, and surprisingly, with probability 1, you will get the same graph up to isomorphism. And there are a lot of other examples. So this theorem somehow captures the idea how to have a limit from a collection of finite objects, how to produce a limit object. Okay, so we'd like to understand the automorphism groups of the Fraisse limits. And for example, in the case of the infinite set, the automorphism group is just the permutation group, which I will denote by S infinity. And this is a Polish group with the usual topology. Okay, and also a well-known theorem is that a Polish group is an automorphism group of a Fraisse limit if and only if it's a closed subgroup of S infinity. Now, some examples, and the most important ones for this talk is S infinity, the automorphism group of the rationals, the automorphism groups of the group of the random graph. The countable discrete groups are also good examples, and we can form countable direct products, and we will still have automorphism groups of Fraisse limits. Okay. So, and our aim is to, first aim is to understand the typical behavior of the elements of such an automorphism group. So we will say that a property of elements is holds generically, or is typical, or the typical element has a certain property if that property holds with a meager exception. Okay? And we are also interested with the conjugacy relation for different reasons. One of them is that, okay, so suppose that we have a structure A, and we have two automorphisms F and G, and we extend the structure with two automorphisms. Then the two extended structures, AF and AG, so these are structures with functions, not just relational structures, will be isomorphic if and only if the two automorphisms are conjugate. So this says that two automorphisms are similar, so they essentially isomorphic if they are conjugate. And okay, so it can happen that that there is a very large conjugacy class. So there is a conjugacy class so that its complement is meager. In this case, we will say that there is a generic element. Right. Okay, some examples of the generic behavior. First, I'd like to say a couple of words about S infinity. So, if we have a permutation in S infinity and a point from the underlying set, then we can iterate this permutation, take P, F of P, F of P. Okay, so this is just the orbit of P, and it is possible that we return at some point, then the orbit will be finite, and I will call this orbit cycles. And so the cycle will be finite, or maybe the cycle is infinite. So for example, a cycle of length 1 is a fixed point. Okay? So, and it is an easy exercise to prove that the cycle structure in S infinity completely determines the conjugacy relation. So what I mean is that if we have two permutations are conjugate, if and only if they have the same number of cycles for every cycle length. Okay, and it is not hard to prove that the typical element of S infinity has infinitely many cycles for every finite cycle length, and there are no infinite cycles. Okay, and this actually the description of one conjugacy class. So in particular, there is a generic element in S infinity. Okay, so in S infinity there is a generic element, and also there are some other results. For example, it is known that in the automorphism group of Q, a typical element has infinitely many fixed points, and also it was proved by Truss that there are generic elements in the automorphism group of Q and in out R as well. Okay, so it is an interesting question whether there exists a generic element. And this question was solved by Kekris and Rosendahl in terms of, they gave model theoretic conditions on the existence of a generic element, and I think it is a quite nice idea. So we would like a generic automorphism for a class K. Okay, how to have one? First we have to develop the Fraisse limit and the Fraisse theory for structures with functions. Okay, and extend this K, or instead of this K, consider the class Kp, which is the following. We have a structure from K, and also we have a function, a partial function on A. Okay? So, and we hope that if this new class has a Fraisse limit of some sort, then of course in the Fraisse limit there will be an automorphism. Okay, so at least some kind of partial automorphism, and we hope that this will be a generic one of the limit of the original structure. Okay, so I think this idea already appeared in Truss's work. So the case is that you have to modify a little bit the conditions in the on the Fraisse class. You have to weaken the amalgamation property, but they gave necessary and sufficient conditions on the existence of a generic element. Okay, so the category case is essentially done. What about the measure case? So first, what is a natural measure on these groups? And by natural measure, I mean left Haar measure. So what is a left Haar measure? A left Haar measure is a left invariant measure with some regularity properties. So we assume that every Borel set can be approximated, the measure of every Borel set can be approximated by the measure of open sets from above, and every open set can be approximated by the measure of compact sets from below. And to avoid trivialities, we also suppose that the measure of every compact set is finite and the measure of the whole group is positive. Okay? And unfortunately, in the existence of left Haar measures, so there exists a left Haar measure in a group if and only if it is locally compact. So non-locally compact groups, there is no natural measure, and the three groups I mentioned, S infinity, the automorphism group of the random graph, and Q are all non-locally compact. So what do we need? We need a notion of smallness which generalizes the notion of measure zero sets in non-locally compact groups. Okay, and this definition due to Christensen, we say that a set in a Polish group is Haar null if there exists a probability measure, some probability measure, which I will call witness measure, so that every translate of this set is of measure zero with respect to the witness measure. And so this is for Borel sets, and for arbitrary sets, for technical reasons, we say that an arbitrary set is called Haar null if it can be covered with a Borel Haar null set. Okay, so clearly this notion is translation invariant. What is not clear that this is a sigma ideal, because there could be different witness measures. But Christensen proved that this is a sigma ideal using convolution. And also, he proved that this is a generalization. So in locally compact groups, a set is Haar null if and only if it's measure zero with respect to a Haar measure. Okay, so this is indeed a nice generalization of the null ideal, but there are some interesting things. For example, Zoltán proved that in non-locally compact groups, this ideal is not CCC. So there could be there could be continuum many pairwise disjoint positive sets. Okay, and we would like to measure the size of the conjugacy classes with respect to this notion. And one trivial observation is that if we have a set B, so that every compact can be translated to this set, then this set is not Haar null. This is obvious because if we would have a witness measure, then this witness measure is positive on some compact set, but we can translate this compact set to R set, so this could not be a witness measure. And the reason why I say this is that almost every time when we prove that something is Haar positive, a conjugacy class is Haar positive, we actually prove that every compact set can be translated to it. So if our results can be used by someone who does not like this notion of Christensen. Okay. And the first results about Christensen's Haar null sets in S infinity were proved by Dart and Michalski. And okay, and so now this makes sense to say that some property holds almost surely. So because there is a notion of almost everywhere or something like this. And Darty proved that almost every permutation in S infinity has infinitely many infinite cycles and just finitely many finite ones. Okay, so this shows that the notion of meagerness and Haar nullness, notions of meagerness and Haar nullness are perpendicular to each other because the typical behavior was that there is no infinite cycle at all, and there are a lot of finite cycles, but here there are just finitely many finite cycles and infinitely many infinite ones. Okay, and notice that this describes countably many conjugacy classes. So therefore, almost every element of S infinity belongs to countable union of conjugacy classes, of some certain conjugacy classes, and they also prove that all these conjugacy classes are Haar positive. Okay, so in S infinity, there are countably many positive conjugacy classes, and their union is almost everything. What about the other Fraisse limits? So we could generalize their theorem in the following way. Suppose that we have a structure A, a set X, and an element of a structure A. We say that A is algebraic over X if whenever we have an automorphism that stabilizes X pointwise, then we have only finitely many options for the image of A. Okay? So this means that there is some sort of connection between A and X. And we say that the structure has no algebraicity if this does not happen except for the trivial cases. So if A is not in X and X is finite, there is no algebraicity between them. And we could prove that if we have a Fraisse limit with no algebraicity, then almost all elements of the automorphism group have finitely many finite cycles and infinitely many infinite ones. Okay, so this is the generalization of the Doherty-Michalski result. And some particular cases, for example, in the automorphism group of Q, what is the situation? So suppose that we have an automorphism group, automorphism of Q, then trivially it can be extended to a homomorphism of the real line. And if we take a maximal interval without fixed points, then we can go either above the identity or below. So such an interval will be called an orbital, and if we go above this, that will be a plus orbital, and otherwise it will be a minus orbital. And it is not hard to show that F and G are conjugate if and only if there is an order-preserving isomorphism between the set of fixed points of the extended maps, and so that this isomorphism preserves the sign of the orbitals. Okay? And what we could prove that there are at least countably many Haar positive conjugacy classes in out Q. Okay, so but we don't know whether there is more or what is the current situation. And also what we could solve that in the homeomorphism group of the unit interval, there are only countably many positive ones, and their union is almost everything. Of course, this is not an automorphism group of a Fraisse limit. So. But someone would think that these two are not too far from each other. Okay, what about the random graph? Again, in the random graph, we have to understand the conjugacy relation. So suppose that we have a cycle. Okay, now we are in the random graph. and here we have a vertex. And check whether the vertex is connected to its image. Okay? And then we check whether the vertex is connected to the image of its image. And so on. So we will have a 0-1 sequence. To every cycle, we can assign a 0-1, an infinite. To every infinite cycle, we can assign an infinite 0-1 sequence. Okay, and it was proved by Fraisse that two automorphisms, F and G, if they have only one infinite cycle, such automorphisms actually exist. So this theorem says something. So if they have only one infinite cycle and nothing else, then they are conjugate if and only if the 0-1 sequences are the same. Okay? So this will mean 1, this is 0, etc. Okay, but we want to know the conjugacy relation for those automorphisms which have infinitely many infinite cycles. There is an appropriate generalization, but the things are quite complicated because if we have two cycles already, then we have to consider the edges in between. Okay, so there will be extra 0-1 sequences according to the edges in between, but this theorem can be generalized. And so if we have a conjugacy class, then the set of these betas for all elements of the conjugacy class should be the same. Okay, so if we have two conjugate elements, then and one has a beta with just zeros, then the other one should have one with just zeros. Okay, and then one would think that okay, to hit a certain 0-1 sequence is extremely unlikely. Okay, and so therefore every conjugacy class should be measure 0 or Haar null. But recently we realized that there are continually many Haar positive conjugacy classes in the automorphism group of the random graph. Maybe I should have put quotation marks around the theorem because it is quite complicated and not written down in full details yet, but I'm rather sure that this works. Okay, and so these are our questions. How many Haar positive conjugacy classes are there, and whether the union of the small classes is still small. Okay, and we would like, and notice that these questions make perfect sense in compact groups as well, and locally compact groups. No, I mean this is for a certain automorphism group. Okay, so so we have to decide these two questions. We want to decide these two fact questions for every given automorphism group. Okay, and we have this table, so we want examples of certain groups. So here we have compact, locally compact, non-compact, non-locally compact groups, and this is the current situation. So a couple of words about these examples. This H&N means, so what is this? We want a locally compact, non-compact group with a finite number of conjugacy classes. This is can be achieved with the so-called Higman-Neumann-Neumann extension. And also it is our observation that if you have an example here in the upper part, then you can turn it to the example in the lower part of the table by multiplying the group with this semi-direct product. Okay, so these three are the most important questions. In particular, this one is very interesting for me. So is it true that there exists a compact group with infinitely many positive conjugacy classes, and it is even more interesting in the light of Vesolek's results, who proved that in a compact group a conjugacy class is positive if and only if it is open. So we have to produce somehow infinitely many disjoint open conjugacy classes. Okay, and this is also interesting, I think. Even though we couldn't decide the exact place of the automorphism group of Q, we could show that the omega's power of this group must have continue many positive, Haar positive conjugacy classes. So we can determine the exact place of this group. Okay, I will finish with open problems. I've already mentioned this one about infinitely many positives in a compact group. Of course, these examples are very artificial. It would be nice to have more natural examples of such behavior. And also, the most interesting question for set theorists, I guess, that we don't know whether it can happen that there are kappa many Haar positive conjugacy classes with kappa between Aleph 0 and continuum. Okay, and finally, the ultimate aim of this research, I think, is to prove a Kekris-Rosendahl-like result to turn this behavior to relevant model theoretic conditions. Okay, that's all. Thank you very much.
Very much. Questions? Martin.
So in those cases where you have continuum many classes, I assume there is in some sense a perfect set behind it.
Yes, yes.
So there's no induction.
No. There is a very nice perfect set of positive.
Other questions? Doesn't seem to be the case. So let's thank the two speakers again.